on that, right?
Yes.
And that's and he will actually give the colloquium on Thursday. And that's a 3:15. That will be done in the Oscar Klein Auditorium. And that will be about the so-called electrostatic sail. It's called electrostatic sail, right?
Yeah.
It's a new invention. It's different from ordinary sails which work in the solar wind. This works based on the repulsion of oppositely charged particles, and the solar wind is, of course, electrically charged. It's also different from the magnetic sail, which is another invention, both of which have their problems. This one works with wires, and is therefore, even if you have some impacts from the meteoroids, they just go through, of course. So it's a potentially extremely powerful thing. And there will be the first test flight launched in 2012. So he will be talking more about this. But Pekka has been doing MHD simulations, especially in the context of magnetospheric physics, global simulations of the pencil code, this is his own code. But your code has a name, right? What is the name of this code?
UMIX.
UMIX, yes. So there's a bunch of people, they're mostly in, these guys are mostly in Helsinki, right? Or is it internationally in use, the code?
There is an installation of the code, the CCMC, this community coordinated modeling center.
Yes, okay. Very good.
You're from university or from FMI?
FMI.
Ah, okay.
Yes, that's Igor Rogachevsky. Maybe other people want to introduce themselves at this opportunity, because we have our chairman not yet. Gustavo, our postdocs here at Karl-Heinz Reta. He will be contributing to some of the discussions today about the cross-helicity effect. Igor Rogachevsky, Fritz Busse from Bayreuth, Emike Madarashi from Stockholm, and Gyali Chatterjee here at Navida, Nathan Clearin, both Igor at the Beersheba, and our organizer Sasha Kozovichev and Irina Kitiashvili, and our speaker and our chairman Matthias Reinhardt and Mitsu Yokoi. So, our chairman, please.
Yeah, I'd like to open the afternoon session with our previous and future speaker, Mitsu Yokoi.
Okay, okay. Thank you for spending so much time for my talk. So my next subject is cross-helicity and its related dynamo. Okay. So here I don't show not so much equations in this talk. So the first thing is I will talk like in these lines. First show what cross-helicity is, and then it presents the dynamos using cross-helicity concept. Then some application will be presented. Then some discussion and some very recent proposals for the cross-helicity observation in solar physics will be presented. Okay, so I hope you already know this, and these are cross-helicities, and this is total amount of cross-helicity, and which is known implicit invariant of incompressible MHD. And also, this is turbulent cross-helicity. I already talked about, and this is the mean field cross-helicity, and we use these notations.
So if it's compressible, then definition is different from cross-helicity.
Incompressible case, as I used in the application of my model to the solar wind case, in the last topics of my morning session, it can be expanded to in compressive case.
Well, suppose now we have a rotational flow field fluctuations, right? No vorticity one. Then what would be cross helicity? But still, if we calculate formally, we still have cross helicity.
Is integral of motion.
Huh?
Yes, integral of motion. Cross helicity is integral of motion with rotation. I'm not sure, by the way, with
No, I mean,
rotation.
suppose we consider turbulence without helicity, without kinetic helicity. But this integral still non-zero. And then
Still
it means
on
you
the
have, you don't have helicity, but you have cross helicity.
Yeah. So I will, as I showed in my outline of my talk, I will discuss with how the situation that cross helicity, total amount of cross helicity is non-zero, some finite cross helicity case, and that's the point I think very important in dynamo action. That's the point. Okay, thanks. So sometimes cross helicity is discussed with Alben wave, in relation with Alben. As you know, if large-scale magnetic field deform, then we have several kind of magnetic kind of fluctuation of like this. This is compressibility related term, and this is a genuine Alben wave, and also some kind of magnetic magnetic sound wave. And as you can easily see, if we have a large-scale magnetic field B, then the wave is propagated along to B, parallel to B. Then we have, as you see, we have this type of displacement. Then we have a negative, in the parallel propagation case, we have negative correlation between U prime and B prime. And in anti-parallel propagation case, then we have positive correlation between two fluctuating fields. That's the point as I talked in the morning session. So in magnetospheres of because of corrugation of mid-plane, the satellite for the solar wind fields, sometimes in one section in inward direction magnetic field, and in some magnetic section outward magnetic field. And always it is considered, very roughly speaking, the oscillation originated from the surface of the sun, near the surface of the sun. So Alben wave propagated always outward direction. Of course, I know there are some argument of inward propagating waves, but anyway, first approximation we have outward. So in the case of
What is the source of turbulence in solar wind? What is the source of turbulence in solar
source of turbulence, it's very difficult, but one of this, if we consider Albenic turbulence, the magnetic activity including some ejection or some, it must be one of the sources of especially Albenic turbulence. My point is that if we have inward magnetic field and Alben wave propagate always outwards, in such a magnetic sector, we have positive cross helicity, as I showed. And in outward magnetic field, then we have negative cross helicity. So this difference is very, very important from the viewpoint of dynamo and physics. But geophysics people, space people always change their sign to negative, positive or something. So they only show is the magnitude of this correlation.
So it determines the direction of the mean magnetic field, yeah?
Yes, I think so.
Yeah?
Yes. And because if we have a perfect symmetry, we at the mid plane we have zero cross helicity because we have magnetic field upper half we have inward, lower half outwards. So at the mid plane we have no. But magnetic field surface is corrugated. Then we have this type of a kind of four sectors.
And if you have velocity shield, I mean, there is mean velocity.
Of course,
then it will be different, I think.
Different. Yes, so that's also a factor to produce the process.
But in case of Alfvén waves, I think this picture is not correct. In Alfvén waves, it's a helical. We change vector magnetic field. It's a three-dimensional wave. That's why I have helicity.
Yeah.
Because of this, it's incompressible. You must have, this motion like this.
Yeah. In case magnetic field, yes.
You can see the same, fast MHD wave, right? Then you have motions like drawn here.
Yes. Especially in a helical torus of magnetic fusion, we from the beginning we have a helical.
This just happened for Alfvén wave because it's intrinsically helical. But say we can see that in your picture what you drawn. It's like a fast MHD wave, right?
Okay.
This is 1D.
It depends on plasma beta.
Okay.
It depends on plasma beta.
What's similar to fast? I mean, even for small beta, it's
No, I think it's, this example, if say, this product is a helicity, it's true for Alfvén wave because it's helical. But the picture drawn is not for Alfvén wave, it's for say, fast MHD wave, right? You got that.
No, but nevertheless, if we just look on this expression, that the integral in K space of this stuff will be almost zero in homogeneous situation. Am I right? Because if you multiplied u delta b on u, which is parallel to u, to zeta, it should be almost zero.
If we have, I'll show these two solution is these two relation is the solution of MHD fluctuation equation. So in this sense, if we totally integrated this solution, it should be zero. But as in the case of solar wind case is only the outward propagating wave is at least dominant. In this case, a finite amount of cross helicity is observed.
But in principle, this should depend on the ratio of gas pressure to pressure of magnetic field, large scale magnetic field. So you consider the situation when plasma beta is large or small. This is a question. Which situations you consider? With large plasma beta or small?
Yes. It depends. So it depends. So it depends where I'd like to apply.
In what place of solar wind?
In solar wind case, is magnetic field is not so strong compared to near the surface of the sun, and also in fusion plasma case. In fusion plasma cases, magnetic pressure is much rather than the gas pressure. Okay, so also the SS using, I sometimes use is SSR variable, and this formulation can be easily extended to the compressible case. So Eckhart Marsh contributed this expansion of SSR variable to compressive case, and I actually used his formalism. Anyway, so this is just for reference. In SSR variables, U plus B and U minus B, Z plus and Z minus, and the quantity cross helicity is equivalent to this plus SSR plus square minus SSR minus square. And energy is a sum of these two, and residual energy I just presented in the morning is something like this. So this quantity is very one essential variables for especially for MHD SSR variable formalism. Okay. So this is related to the Axel mentioned morning. So you can refer to Moffat's book and some papers. Cross helicity is that directly related to the knottedness of magnetic flux tube and vortex flux tube. So the conserved property of cross helicity in MHD equation indicates the knottedness. Number of knots is conserved in implicit case. That's a geometrical interpretation of cross helicity. If we put instead of magnetic flux tube, both are vortex tube, then we see this is helicity, kinetic helicity. Okay. So there are several properties of cross helicity. So one very important one is cross helicity pseudoscalar, as I showed in the morning. So velocity is polar vector, and magnetic field is axial vector. So to the reflection of the plane, so cross helicity transformed as a pseudoscalar, like this. And in mirror symmetric system, by definition, we have mirror symmetry of the quantities. So pseudoscalar in mirror symmetric system is this is pseudoscalar, and this is mirror symmetry. Then we identically zero pseudoscalar. So that means in mirror symmetric system we have always vanishing of pseudoscalars. And so vice versa, non-vanishing pseudoscalar means there is some breakage of mirror symmetry in the system. So cross helicity can be a measure of mirror symmetry breakage. Okay, just as the helicity and magnetic helicity can show the breakage of mirror symmetry. Okay, so there is another very important, practically very important properties of, as I already mentioned in the morning, there is some boundedness of this quantity. So it is practically very important. So because this is just saying like this. So as I mentioned, we construct the equation for K. This itself is very exact form, and also can write most very same equation for the cross helicity. Then this is also exact. Then we can construct the equation from W over K. Then exactly seen like this. So in the case of, for example, homogeneous case, we have no production and transport term also vanishes. Then we have for the dissipative parts of this quantity, we have this quantity should be positive because W over K should be bounded. So then we have some information for the dissipation rate of cross helicity ratio to cross helicity dissipation to energy dissipation, like this. So this is very important to
How would you write the second equation? You write just by analogy, the second equation for
this
W.
one. This
for
one.
W. The second,
Second.
yeah.
This is exactly derivable from emitted equation.
And what is PW?
Sorry. I will show it. So sorry. PW is production rate of cross helicity.
Of course.
I will show soon. And the point is that, as I mentioned, I'm not sure. This quantity is conserved quantity, and also this quantity is conserved. So it's turbulent counterpart.
How do you know it's conserved? How do you prove this?
Just derive equation for.
Conserve in what sense? If you got ideal hydrodynamic, without dissipation, and flux equals 0, in this situation it's conserved.
Eta or lambda I.
So it's
If we put nu viscosity and magnetic diffusivity are 0, then this equation for this quantity is written like only divergence related term. Then without any special input from the boundaries, we have already this quantity is
How do you prove the second?
same,
The same.
exactly the same. If we something like this, so
It's probably only for incompressible. Is it for general people only incompressible? Because it follows from induction equation, right? There's induction and momentum, iteration momentum equation, right?
Maybe compressibility destroyed.
Obviously, when we know
If it's compressible, then
I think we should take into account rho. It is it should be something divided by root square from rho. Root square from rho. It should be. I think it will be the same. As in energy, you take rho u square. So it's more,
Yeah.
something in this.
Yes, exactly. So you have to use new variable like b divided by rho, and then in the case of compressibility, conserved quantity is u multiplied
By the root from rho. It will be u dash.
No, it's not root Natan.
It's true.
Because for compressible flow, For example, we have for zero resistivity, we have frozen condition for the magnetic field. In the case of compressibility, frozen condition will be for variable B divided by rho.
Right.
I don't think
And the same integral of motion will be for the same quantity.
no,
Is it correct, Axel?
I mean, you're saying you have to replace rho by u by something else? I don't think
No,
that's
no, no,
correct.
no, no. I mean, well, remember,
But just don't figure. Just a
frozen
minute.
condition.
If energy is another will be, if rho not constant, it will be u square multiplied by rho. It's energy, right?
But that's not what I think
Rho
about.
multiplied by u square, energy, should be, for compressible case, energy is not u square, rho u square.
I must ask what you're talking about crossolicity, right?
No, no, I think we should replace both integral of motion.
We speak
You don't know
about the
what you're talking about.
conservation
Are you
of
talking about
quantity for
crossolicity?
compressible case.
Not only cross
Hmm?
We speak about conserved quantities in the case of
Sure.
compressibility,
And I think
which is
it's,
non-zero.
and I think it's u dot b integral. Just
U
as
dot B integral.
yes,
Yeah.
and the reason is that you have the momentum equation there. You have J cross b divided by rho.
Yeah.
But you dot this equation with b, and so the whole term drops out, regardless of whether there was a 1 over rho or not. And then you have terms from u dot by u. There's no rho anymore, because you divide the entire equation by rho. And you just have a term there with b, and you have a corresponding term from the induction equation. Again, there is no rho.
But
So the only thing has to do with the pressure, occurrence of pressure terms.
yes, it's a problem. If you, you should, how to say, multiply equation of motion by rho, to put rho into total derivative, and just after that, recalculate for all integrals. And I think it will be rho u b, and definitely energy will be rho u square in this situation. Rho u square.
So we can maybe
Okay.
Okay, we can check after.
Okay,
that.
again, rho, I think it's
Yeah. And again, I have this type of division to the mean to fluctuation. And as I mentioned, the mean velocity equation is written like this. Pm is magnetic pressure, mean part of magnetic pressure. I mean gas pressure plus magnetic pressure. And this is MHD, Reynolds stress. And also we have tablet electromotive force. And in the case of incompressibility, we have and I skip the derivation of this expression, but especially Reynolds stress. But it is known from the statistical theory of MHD tablets. In our method, Reynolds stress can be written like this in using scalar coefficient. And of course there is some other term appears, but written like this. And also turbulent electromotive force is written like alpha term and beta term, and this is a cross-helicity related term. So and also this nu k is directly related to beta, and this nu n is directly related to gamma. So we know that I will show a very intuitive derivation of these quantities. But from the statistical theory of turbulence, inhomogeneous energy turbulence, alpha is expressed using turbulent residual helicity, just like 2K showing. And beta nu k is turbulent viscosity. And turbulent diffusivity, magnetic diffusivity is expressed using turbulent MHD energy. And gamma and mu n related to magnetic strain in Reynolds stress can be expressed using cross helicity. So we can model this quantity using some time scales multiplied by helicity, time scale multiplied by energy, and time scale multiplied W. And original.
I'm sorry, you use maybe in other notations. In previous talk,
Yeah.
you denote gamma as a cross helicity.
Yes.
And here, doesn't use cross helicity.
Yes, that's exact. Gamma is not cross helicity.
Okay.
Gamma is something like this green function
Yes.
and spectrum of UV and time integral and something like this.
And this is gamma.
Gamma.
Uh-huh.
I don't know. Yes, this is gamma. So gamma itself is not cross helicity, but we can easily model using this expression. Gamma can be expressed cross helicity multiplied by time scale.
Yeah. But we see that gamma is related only with magnetic diffusion. Why gamma is independent on kinematic viscosity? No, not kinematic, turbulent diffusion.
Gamma?
Yes, gamma. Gamma proportional to 5 cells multiplied by the
This
mu m.
mu m is not mu k. Mu m is constant for.
Yes, this is a magnetic diffusion. Is it correct? Or
Yes.
This is
No.
turbulent magnetic diffusion. No?
It's like the,
No.
it's like the Shunya effect.
No, this is not connected to magnetic diffusion is connected to nu k beta. So this is a kind of turbulent 5/7 is a kind of turbulent Prandtl number.
Okay.
So this relationship itself has been already derived using renormalized theory of RLG analysis of MHD equation. Anyway, my point is, in this point, alpha coefficient for large scale B is time scale multiplied residual helicity. That's one point. And beta related to turbulent magnetic diffusivity is related to energy multiplied by time scale. And also gamma is only appears here and here. Is related to process. And tau itself can be estimated using green function formalism, using the result of theoretical. But
so mu m is a new transport coefficient, yeah?
yeah, mu m, also gamma and k beta, these are all transport coefficients.
Also you have B, capital B 0. And you have only,
Yeah.
you have only capital U.
Yeah.
Then without any magnetic field, you still have electromotive force.
Yes, if we have even if we have fluctuating magnetic field, even without large-scale magnetic field.
That's of course why we talk about battery, because it's a battery for the mean field.
But gamma is independent of magnetic fluctuations, or it depends. Gamma depends on magnetic fluctuations or not? This question.
If it depends on fluctuation, then
Gamma is proportional to the cross
Equation
helicity.
is
So if there's B dash, it's fluctuation. Depends on magnetic fluctuation.
then this equation is meaningless.
Gamma is, basically speaking, gamma is expressed like this.
When you derive this equation for electromotive force, the purpose is to express fluctuation in terms of large scale. property, right?
But Serge, it's not electromotive force. If it's for electromotive force, interesting opposite component of this correlator.
EM is electromotive force. EM.
EM is electromotive force, a W is not electromotive force. W equals 0 for ideal electromotive force, then U cross B maximum, U dash B equals 0.
Okay, so
Because that means you have dynamo without anything.
It's possible.
yes,
Just
yes.
partitioning and then you have dynamo.
It's
No, it's not for this.
But
It's
still,
Maybe
just
that's
curl
one
U,
important-
curl U, and
sorry.
then you have dynamo.
Yeah, yeah.
Maybe one thing is
No,
not
it's interesting. There's something to it.
Huh?
But how to do it? You know,
This is
No, no,
Yoshizawa effect.
only a second. Maybe one thing important to stress that you are considering circumstances in which already without the mean magnetic field there is already a fluctuating
it's
magnetic field.
possible.
This is not always done so in models, but you do so.
It's possible.
And that's why there isn't
But that's
an arbitrary
situation meaningless.
magnetic
No, no, no.
already there
Okay,
without the mean
it's
field.
clear.
This answers your question.
No.
I see that it's
Then I
here.
say, wait a moment, then I say it again.
Because the purpose of this equation is to express fluctuations in terms of large scale parameters like
Yeah.
alpha effect, right? Alpha doesn't depend on fluctuations. It's something that some properties of the medium.
Yeah,
So gamma is also properties of the medium.
yeah.
And if
Not
gamma
the
depends on
medium, turbulence.
d prime, then this equation is meaningless.
No, no,
What equation?
no. No, here B.
Gamma must be a property of the medium.
Here magnetic fluctuations.
I know
It's
one
not a
example.
property of the
So,
medium, it's a
situation
property
is
of
not
turbulence.
obvious.
Turbulence.
Here there is no any small scale dynamo. So there is only one source of generation of magnetic fluctuations. Just tangling of the large scale magnetic field by velocity fluctuations. If mean field equals 0, then gamma equals 0.
Igor, I am ready to give you example. It's not true. For example, if we've got fluctuation
yes.
of
Sorry.
electrical pressure, fluctuation of pressure of electrons.
Okay, fine. I speak about the framework of one fluid MHD.
Okay, no Hall effect. If
No Hall effect. If there is no Hall effect, gamma equals identically 0 when mean field equals 0.
Right.
Is it correct or not?
I think it's correct.
Okay, fine.
I suppose such situation
How do you
because
on what?
yes, without mean field, mean magnetic field, I think it's very difficult. I need some special source for fluctuating.
Let me say nevertheless how to say one idea in the new defect, if you like. If you remember in previous our program, Anik Fouquet lecture, you remember that they find for small scale dynamo on nonlinear stage similarity between magnetic field and velocity field. So it means for small scale dynamo it's plausible, at least for some scales at least, that U dot B is not equal 0. U cross B, yes, equals 0. Without mean field, it's impossible.
But how to produce B fluctuations
Yeah.
magnetic field?
Due to small scale dynamo.
Okay, so if there is small scale dynamo, this is other.
Yeah,
But I'm not sure.
I don't know what mechanism can produce such fluctuation without large scale B. But if there is some mechanism to produce B fluctuation, then it will present. But I myself are not so interested in such a situation. But somehow, yeah, you can consider such situation, especially some source term or something. I don't know. So the point is also the same one. This is the same equation I showed you in the morning. So for me, the primary effect of turbulence is enhancing diffusivity, molecular diffusivity. Spitzer diffusivity is enhanced by the presence of turbulence. That's the primary effect. Then if we fortunately have some symmetry breakage in the system, then we have some other terms like alpha term and also cross-Helsty term. And yes, so this is the same one I showed. So then I will show physical interpretation of dynamo effects. So thanks to Karl-Heinz, this type of figure is very famous and useful. And but in this talk, I don't resort without resorting this time of figure. I will consider each term separately. Okay, so this first I will show you the cross-helicity effect. This cross-helicity effect itself was calculated using statistical theory by my supervisor Yoshizawa. And when I discussed with this effect with Gene Parker, he would like to see the physical interpretation of such effect. Then I consider this one.
But this effect can be also obtained in the framework of first order smoothing approximation. Is it true?
Yeah.
Yeah, okay. Okay, fine.
If you assume MHD turbulence.
Yes.
Of course,
Small
no
scale
doubt.
Yeah.
So this implies that this effect can exist also for small magnetic Reynolds number.
Yeah.
Small Reynolds number.
Yeah.
Okay, fine.
Okay, so just consider the fluid particle in the large-scale vortical field. Then we have large-scale vorticity. Then we consider fluctuation, and we assume a positive cross-helicity in the turbulence field. This is assumption. Then by definition or by assumption, we have in a statistical meaning we have magnetic fluctuation parallel to velocity fluctuation. This is assumption. Then this fluid particle are subject to the Coriolis-like force due to this vertical motion. So this is accelerated this direction. That is secondary velocity field. Then we construct the electromotive force due to delta U and B prime. That's this direction. So my point is that if we have a negative cross-helicity, this will in anti-parallel direction. So this is my interpretation of cross-helicity effect.
Yeah.
When the average is just one.
No. In any direction. In any direction. We have, if we assume the positive, we always have parallel electromotive force due to this.
But if you multiply this delta U dash to B naught, you should vector product, because for electromotive force you need vector product. Yes, it will be. Of course, it's true.
I think that there are general reasons for that. It's impossible to produce this effect, Yoshizawa effect, by means of small-scale dynamo. Because small-scale dynamo is isotropic effect in the sense, and by means of small-scale dynamo it's impossible to produce preferential large-scale vector.
Igor, it's true.
So this implies that you need to have mean field.
Igor, it's true if without rotation.
Without rotation.
But if interesting, this rotation doesn't, how to say, appear in small-scale dynamo, but it's appear in equation of motion. Am I right?
Well, there is a difference between
Just
velocity and rotation.
Just a moment. You solve your equation for dynamo. You find your magnetic field. We know from, at least from calculation of Anik Poquet, that U dot, it's U dot B is not equal 0. Now you take equation of motion, equation with Coriolis force, you immediately produce this term.
You cannot rely to numerical simulation by an equal k because it may be simulations not turbulence are just appearance of chaos in dynamical system.
No,
So, but I think from the general symmetry reasoning, it's impossible to produce this new effect, Yoshizawa effect, by means of small scale dynamics.
I
Igor?
still don't.
Yeah.
Is your argument not similar to that? You say, is isotropic turbulence cannot produce an alpha effect because you have isotropy. But if it works together with a mean magnetic field.
No.
Rotation.
I mean the following: without mean magnetic field, you don't have any alpha effect.
Yeah.
Because alpha effect is produced if you have mean magnetic field, even small.
And here you are in a rotating system, or you have a vorticity, a large scale vorticity.
Okay,
And
we will
it
continue.
disturbs isotropy.
Okay, I still don't understand what you mean to say, but my point is that in the presence of the large-scale vertical motion, if we have correlation between U and B, U prime and B prime, that's cross-helicity assumption, and also the large-scale vertical motion. That means Coriolis force. That means local angular momentum conservation. Then we have, in the case of positive cross-helicity, we have electromotive force due to these factors always parallel to omega. So this is one explanation, and we can also apply same argument to other effects. So this is a better effect, and so how to say? So if we consider the large scale current field, electric current, that means so B is some rotational configuration. Anyway, if we have fluctuation in any direction, then we have the magnetic field due to this term related to gradient of B. Then we have delta B prime in this direction. Then we can construct U prime cross delta B anti-parallel direction. If we assume non-zero fluctuating velocity field. And also, if we consider the magnetic fluctuation in the large-scale electric current field, then this must be much easier if we consider the Lorentz force of J cross B prime. Fluctuating Lorentz force is always in this direction. Then we can construct delta U prime cross B prime in this direction. So in this meaning, kinetic fluctuation and magnetic fluctuation always works for the anti-parallel direction. That's the reason the electromotive.
Okay, I'm a bit worried by the statement that you have the beta effect due to mechanical fluctuations and due to magnetic fluctuations. U square and B square. In a very old paper by Weinstein, it was shown that there is no magnetic beta effect. Only the part proportional to U square.
For small
And
energy.
it was also, sorry?
For small magnetic energy. This result is valid only when the energy of mean magnetic field is much smaller than the mean magnetic energy. If you obtain,
This is true. It is also, what I wanted to say is this result is also confirmed in Soka and also in the tower for
of course.
Our joint paper,
of course.
we had the same effect.
Of course. But this is for the situation when the energy of mean magnetic field is much smaller than the turbine kinetic
So,
energy.
no influence of large-scale magnetic
Yeah.
field on motion.
Yeah,
If yes,
exactly.
it will be enough.
And of course, this
Why
point
is
is
it-
related to the next graph.
Okay.
So
Okay.
very recently, Axel and Subramanian wrote a review, and in that, and also my colleague Hamba wrote a paper on this, and they showed that's only the kinetic fluctuation, Bell's fluctuation that is responsible to the magnetic diffusivity. But as I mentioned at the lower part of the previous one, if we have magnetic fluctuation, we have some contribution to this one. And I consider, I don't know exactly what, how Axel derived this result, but I consider some intuitive interpretation.
We also derived this result in 2000.
Oh, okay.
Before.
Sorry.
I mean, before that, this goes back to Diamond and
Before that,
But Karl-Heinz, I understood now Karl-Heinz is saying that it was already derived by Weinstein, what,
Okay,
71?
it was derived by Weinstein
Yes.
in the approximation when energy of mean magnetic field is much
Yeah, but
lower
then it's of
than
course
the
standard.
kinetic energy.
Standard.
It might be, but
Einstein derived.
but then you should have a parameter. Beta should not simply proportional to u square plus b square.
No, correct.
There must be some
Okay.
parameter which which is small in the case of small turbulence energy.
Yeah,
Also.
okay, yeah, exactly.
Okay.
Yeah.
So the conditions were clearly just a second order correlation approximation, completely standard. And of course,
Yeah, okay.
Say again, what Weinstein derived you mean?
this I don't know, but
A contribution of magnetic fluctuations to magnetic diffusion. It was, okay.
Right. But it was,
Weinstein was.
but I think it was wrong, unfortunately.
Yeah,
Because he found
Yeah,
that contribution even in case of very small magnetic field.
Yeah, yeah.
It was wrong.
yeah.
He made some mistake when he dropped pressure, I don't remember
Yeah, yeah.
something. It's
Okay.
huge.
But then we made the same mistake in our.
No,
We
no.
improved, and Karl-Heinz, we improved this mistake in our
No, no.
joint paper.
No.
So,
Okay.
And I mean, this is an effect which really comes about by cancellation of at least 3 different terms. So it's non-trivial that it's zero.
No, because just.
So any with a
Station is
pictorial
the
argument, you can easily convince yourself of the existence of one of the 3 terms. But all the-
There is a coefficient which proportional to this parameter. And this multiplied by b square. This is just, there are other, but if, maybe function is this. Okay, and this function tends to 0 in the first order expansion. That's why we haven't got such contribution. But if you take into account other terms, you immediately obtain contribution.
I could agree if you.
Yeah. Exactly,
Consider
so there is a
turbulence
agreement
influenced by the
between-
magnetic field, you would have such terms.
Yeah.
But you have never, or in general, you have not the sum u square plus b square.
Ah,
it's not some, it's more,
Yeah,
much more
of course.
complicated.
but okay, it doesn't.
As I will show, it's a very, in some sense, very complicated effect. So if we have J field, as I mentioned, we have some rotational B, inhomogeneous B, like this. So we, in the upper one, we consider only J cross B prime. But in this case, we do have the large scale B. So the fluid particle feels this effect of large scale B. So we have to consider J cross B, J prime cross B also. And if we have some fluctuation, consider some fluctuation of magnetic field, just like this. Then there is associated J prime, like this. Then we can construct J prime B like this. Then we have in this side of field the fluid particle field like this, concentrated. On the other side, fluid particle subject like this. Then the pressure of this side is larger than the other side. Then there may be some forces to that direction. Then we have delta U prime cross B in parallel direction. That may cancel to some extent to this anti-parallel effect. That's at present my understanding of this effect. So from this derivation speculation, we can see this effect is a kind of higher order one. But anyway, we should care.
And what is the reference on this higher order effect?
No.
2008?
No. Higher order. Hamba derived some.
This higher order effect?
I think you was a referee of this paper. I guess so. So
Okay, but this result is obtained before.
I don't know. This effect was considered by me, so it is really higher order one. But Hamba and Sato, physics of fluid or physics of plasma.
Actually, what's the question? Where is the first correct description of this phenomenon?
It's true.
I think we're talking about the limits where this P bar is small.
Yes, indeed.
No, I said we derived this equation for arbitrary ratio.
Sure.
Okay? If we consider limit of our result to the case when this parameter is small, b large,
Yeah.
then this contribution vanishes.
Yes,
And the next
but is that in agreement with what you're saying? I think not.
I'm not sure about.
But we can, okay, we can see.
We discuss it.
We will discuss.
Yeah.
But it's not so important. This effect is not so large because, you know, if you have, for example, small-scale magnetic fluctuations, due to the filling factor, this contribution to magnetic diffusion will be small. So while we speak about this, so
You mean this contribution? Which one?
Yeah.
Which one? This one?
yeah. It's understandable, but it's not so.
Yeah.
So for dynamo, it's not so crucial. Main contribution to turbulent diffusion or turbomagnetic diffusion comes from the velocity fluctuation. That's it. Most interesting question here is really if exists a fact if electromagnetic force is non-zero in the case of zero mean magnetic field. This is most exciting question.
You know, maybe it's interesting nevertheless, because the normal asymptotic for large B, 1 divided by B in third power. And this term, due to this ratio, will be just 1 divided by B. I remember when we
It
find.
depends on
So
which
we'll
field.
find something. It's not so. It's not.
Yeah.
It's not so trivial just to talk with it.
Okay. So let me
Okay.
So this is intuitive interpretation of alpha effect, and this is almost the same by Parker's one. So I think so. If we assume positive kinetic helicity in the large-scale magnetic field, then we have by assumption we have the statistical correlation between U prime and omega prime. Then we have by this term we have this direction contribution by this difference between the lower and upper velocities. then we have this contribution. Then construct U prime cross delta B, then we have in the case of positive kinetic helicity, we always have negative anti-parallel contribution. And in the case of current helicity, same and positive current helicity is assumed. Then we have Lorentz force, fluctuating Lorentz force. Then we have derived this way. So delta U prime cross B is always positive, a parallel direction to B. So that's the reason we have this is minus sign and this has a plus sign. So in order to estimate time scales, we need some estimation of Green function. But anyway, so my point is that as of course I know this type of argument is sometimes very dangerous. Just the beta effect shows we may have dropped some very essential terms, but still I think this kind of effect deserves to consider in the case of large-scale vertical motion.
So omega is vorticity here.
Pardon?
Omega is vorticity here.
Omega is vorticity.
Large-scale vorticity.
And as you know, large-scale vorticity is equivalent to rotation. So, yeah.
This argument is very good if you know answer before your calculation.
Yeah.
Okay, so we said so the combination is very important. So as I mentioned, beta effect is always appears if we have large fluctuations. Of course, we assume some presence of large scale B, but anyway, this is always appears. So if we have negligible contribution of this cross-helicity related term, we have a balance between alpha and beta. But we have negligible helicity effect, we have a balance between these two terms. And this relation, balance between B and J is related to this situation.
You know, it's very interesting. Your simulations and simulations by Shikachikhin with shear dynamo can be explained only by this effect. Because we consider, sorry that I interrupt, but it's a very interesting moment. If there is only shear, turbulence with imposed shear, then there is vorticity. There is generation of large-scale vorticity due to the vorticity dynamo. And growth rate of this vorticity dynamo is very huge. So, without this term, without alpha effect, it was demonstrated numerically by Axel and by simulations Yosef and then the simulation. Just a moment. That I think that this effect.
It's not dynamo because no exponential growth of magnetic field, just linear.
Where?
If you've got just this term, it's not proportional to magnetic field.
Combination of this term with shear produces large-scale dynamo.
No, it is again, listen. This term is linear in magnetic field.
So linear?
Linear will be linear. I mean, increasing will be linear in terms of time. This because it doesn't depend on magnetic field at all.
It depends on the mean magnetic field. Depends. Gamma depends on mean magnetic field.
Oh, why it depends on mean
That
magnetic
assumes
field?
that gamma is, of course, independent of B bar.
Yeah,
Now,
normal.
in the simulation with Sharon Shua and myself earlier this year, that was not the case. So if you do the so-called no cosine or the Atlantis flow, gamma actually turns out to be dependent on B bar.
If it depends, it may be, but if not depends, not.
Yeah, if not depends, but gamma equals 0.
It's quite natural that everything depends on B bar. The question is, do the coefficients go to zero
Yeah,
in B bar or not?
No,
And
my
this is not
statement
true
is
for
that
gamma.
it should be zero.
Yeah.
If B bar equals zero, gamma should be identical to
No,
zero.
not if you have a small scale dynamo.
But even if you have small scale dynamo, it will be zero.
Correct?
No.
Do you want to say
No,
something?
of course not.
I think it is
You
wrong.
have proven for this? If there is small scale dynamo, gamma.
It's not equal zero.
No, no. I mean the following: if large scale magnetic field equals zero, identically,
Yeah.
and you have only small scale dynamo, so your statement is that gamma is non-zero.
Yeah. The gamma depends on the cross-helicity, U dot B.
Okay.
average.
And
And if you have something, say, a small-scale dynamo which produces a cross-helicity, then
as
gamma
far
is
as I know
Exactly.
from simulations, cross-helicity equals zero.
Yeah,
For
normally
small scale
yes.
dynamo.
Yeah, of course.
Yeah?
So normally, hey, but wait, normally you are right. But you don't have to be right. There could be circumstances where you
I
are not
don't-
right, but we
I'm
have
not
not
sure.
really found those, not at least commonly. There's
So-
only very few cases that you know of.
So up to now, there is no any improvement,
Yeah, but that's not
even numerical,
Yeah, but
that gamma
of course not.
is okay. Fine. Sorry.
But that should not be taken as a kind of criticism. That would be, of course, wrong.
No, of course, sounds better.
Yeah.
Okay, so I will discuss some generation mechanism of the cross-helicity. This dynamo, cross-helicity dynamo we call, can be written like this. J is aligned to omega. J is aligned to omega. Then it is highly probable that B is aligned to U. So we have positive large scale cross-helicity. I mean, mean field cross-helicity is positive. Then with cascading, we have positive turbulence. Anyway, so this is so there is some basic properties of cross-helicity dynamo. So one is that we hereafter we drop alpha terms, then consider the property of this one. One very important one, which is derived by me and Yoshizawa in 1993, is that this B equal beta, gamma over beta U, beta is related to K and gamma is related to cross-helicity. K is emitted energy. So this is a special solution to the stationary state of data. Because if B is aligned to U, it is of course, some approximation like the spatial not so much variation of these coefficients.
But U equal constant in this situation, according to what you wrote, right? So it means that homogeneous velocity.
Of course, the basic fact is J is aligned to omega. Omega. So the presence of omega is essential. So there is a very big step from here to here. This is, but still, in some situation, this is a special solution, stationary solution to this equation. Okay, that's one point. Okay, so the other property is that, so as a consequence of this solution, if we have a mean scale motion with symmetric mean scale motion with respect to equatorial plane or mid plane, then we have a magnetic field B and B in anti-parallel direction. Because cross-helicity, the most probable cross-helicity distribution is anti-parallel. Because cross-helicity is pseudo-scalar. So one mechanism, cross-helicity, such a distribution of cross-helicity is produced is this. we have. Sorry, so where? Sorry, I will show soon. But we have some production term like this. So if we have turbulent energy inhomogeneity along the B direction, that means typical direction is like this. We have some.
This is production for cross helicity in the equation for the cross helicity.
Yeah. To say exactly, this is not production coming from transport of extra. But anyway, this
because you promised us to show what is the production in the equation for the cross helicity.
This can work production like. So that's the meaning we said 3. There are one and two production.
Okay.
And this is but still very interesting term. So if we have large scale toroidal field thread through the disk with, for example, we have in mid-plane we have a large fluctuation, and the fluctuation is decreasing. Then we have from this term positive production of the cross helicity in the upper half and negative in lower. Then we have with symmetric motion we have parallel and anti-parallel magnetic field with respect to mid-plane.
That's some question. We demonstrate stationary solution, as I understand. B equal gamma divided by beta and U. But dynamo for definition, exponential growth of magnetic flux. Is it possible to demonstrate this stage, or what does it mean? You in parallel increase B and omega vorticity. So it's in some sense it combined magnetic vorticity dynamo.
And also, for example, there is a turbulent diamagnetic velocity, which will push out magnetic field from the region of generation. So you understand that there are other effects which will act against dynamo, like the turbulent diamagnetic velocity. Because you have gradient
of course.
Yeah.
So to see.
But coming to Nathan's concern, I think for the first glimpse it is true that one should not speak about the dynamo. So there is a battery, and we have a forced or driven magnetic field which reaches a saturated state. So for the first glimpse, if we don't take the gamma U term, gamma omega term, to be dependent on B mean, then it is not a dynamo. It's simply a
But
force
is it possible another possibility, Matthias? If we
Which
take two equations for velocity and for magnetic field, it will be growth rate mutual. But I don't understand until now from this.
But maybe with the vorticity dynamo, you produce then magnetic dynamo.
You need exponential growth.
We should, yeah.
At present, as far as I am concerned, I use the word dynamo very broad in a broad meaning. So in this, as I showed, this solution is a stationary state.
Right.
So my concern is the sustainment phase of with irrespective of, despite of the beta effect, if we have this gamma effect, cross helicity effect, we can sustain some magnetic. So
maybe it's important to say that the saturation to that state is not due to back reaction. As
Just dissipation.
Consider.
So it's not dynamo in our understanding.
Okay, but
Okay, of course, but
we have another one.
yes. There is no magnetic field here.
So without resort to any omega effect, we can construct this. We can explain in the configuration of anti-parallel magnetic field with respect to midplane. So another point, why have the cross helicity effect being missing? One is that this is my opinion. So one is that very early stage of equation, sometimes by Galilean invariance. So U is set to Z in many textbooks. So that's the first one. And the second one is that so in the case of large cross helicity, we have only small electromotive force. So in the case of large electromotive force, cross helicity effect should be very small. This is the second argument. The third one is that maybe so only the rigid rotation can be produced. Is nothing to do with the large scale magnetic field. That's the third argument. And fourth one is that related to your arguments maybe. So only small amount of cross helicity is observed numerically or observation. That's the point.
And they are absorbed only in the presence of the large scale magnetic field. Yeah? This question. In numerical simulations, non-zero cross helicity is absorbed only in situation with the non-zero mean magnetic field. Yeah? Is it correct or not?
I will show. But
is it correct that non-zero cross helicity is absorbed only in turbulence with non-zero mean magnetic field? So this is the question.
I think that might be true for two cases that I remember now. There is, however, the possibility of magnetic driving. You can have a driving force in the induction equation, and that you could arrange however you want.
Like forcing?
Yes.
In induction equation?
But
Forcing in induction equation. Yeah, but it is such
You mean this? You have a small scale dynamo. Yeah.
Sorry? No.
You assume you have a small scale dynamo. Is then the process?
No. I mean the following. Okay, but maybe we use different definitions. By definition, small scale dynamo is a dynamo with zero mean magnetic field.
Yeah.
Okay? So my question was, is it in all known numerical simulations, the cross helicity was measured explicitly? Somebody observed, is somebody who observed situations with non-zero cross helicity, but with zero mean magnetic field?
the answer is probably indeed no.
No, okay.
For now.
For now, I mean for now.
okay, so there is some answer to these arguments. So one is that Galilean invariance. So to put u equals 0 in very early stage is very dangerous because this treatment also
What's impossible?
this situation. So that's one point.
Yeah.
So second one is anti-correlation of u cross beta and u dot b. So my point is that the important things to consider is a balance between these terms. Especially we have this primary effect of turbulent magnetic diffusion. So my point is that balance is very important. So even if it's very small, or sometimes it's very big, but that doesn't mean necessarily each term is small. Each term is small. So with very large diffusion, turbulent diffusion, and with large generation, but still this is sometimes very small. So that's my point. So what we have to consider is balance between these terms.
But you know, the situation depends on how strong mean magnetic field.
Yes, of course.
If mean magnetic field is strong, total alpha effects tend to 0.
Yes.
Yeah.
I don't deny.
Yeah.
So the third one is irrelevance of rigid rotation. But with rigid rotation, of course, turbulence property will be altered by rigid rotation. And also, with rotation through the boundary, helicity and cross helicity can be injected in some, or sometimes distributed. Even the total sum is zero. We can, in the northern hemisphere, maybe positive on the other. So with rotation, this type of things can occur. And the fourth one is vanishing of processes. So small, one point is small amount of cross helicity may be sufficient to maintain some magnetic field. I will show using cross helicity upright galaxy dynamo upright. And some also breakage of symmetry is needed. I mean, so now we have to consider how cross helicity will be produced. That's the second stage. Okay.
Yeah.
Short course is fantastically interesting.
So what about
Yes,
10 or 15
What is
minutes?
your possibility?
15 minutes? Okay.
So,